Welcome back. We are still talking about section 1. It's kind of the section that never dies, but there's a lot about functions here. So we are on to subsection 3, which has a focus on graphing. So we will be looking at how to draw the graph of a function on some suitable domain. We will also look at domain and image of a function defined by, and here we're going to focus on the graph side of this, because we've already thought about tables a little bit. And then one review or prerequisite objective is to sketch a graph of a relationship between two variables defined by formula, table, or words. So in this case, we'll be looking at all of that. So graph of a function. So this is not actually different really than the graph of any relationship. A function is just a special type of relationship where, remember, given a particular input, it's going to go to exactly one output. So when we're thinking about graphing a function, this is kind of our go-to setup where Q is our dependent variable, the output, T is our input variable, the independent variable. And where you might think of this as XY, this is like TQ. Again, I know this is a little bit annoying, but I've chosen this setup on purpose to kind of shock you out of your normal routine with the X's and Y's, because I think it's worth thinking about. There's nothing special about the letters X and Y. I'm using T and Q. So it's a plot, so a picture in the plane of all the points that look like T is the input and then f of T is the output. So every combination of input and output that this function can take on. So as a concrete example, let's let this be R of S. So we've picked a new letter other than F. Very scandalous, I know. So this is R of S, and the reason we picked R is because we're talking about heart rate. So I think R for rate fits. The letter choice helps remind us of the function that we're actually working with. And then the speed is S here. So R of S would be the speed, or the heart rate at a particular speed of the jogger. So here's our table. We've got our first row that represents the speeds. I did try to shake up the table presentation a little bit. We can write them vertically, where you have inputs in one column and outputs in another column. We can also do it like here, where you have inputs in a row and outputs in another row. So this is that second presentation. Speed in the first row, so 0, 5, 10, 15, 25 kilometers per hour. And heart rate, so we have beats per minute, and these are the outputs that go with them. First, we're supposed to use function notation to write the jogger's heart rate at 10 kilometers per hour. I think this is mostly some interpretation, and this class, maybe more than other college algebra classes, does have a decent amount of that. We really are trying to get at the translation side of math. So 10 kilometers per hour, I guess whenever we run into numerical values, I want to ask myself, what variable here could this possibly represent? There's some number potentially being assigned to a variable. What could it be? So we've got two choices. So if you guessed, there's a 50-50 chance, but 10 kilometers per hour is not a heart rate. That would be a weird way to measure heart rate. It is a way to measure speed of travel in a linear direction. So that seems like it is a good choice for S. And so maybe I'll make a little note to myself that that's what we're really up to here. And then for the jogger's heart rate, again, what we're thinking about is assigning this to some kind of variable. What part of this problem does this correspond to? So jogger's heart rate is R of S or Q, however you want to think about that, because they are the same thing. And yeah, so we're supposed to use function notation, and basically all we're doing is kind of chopping away at the words here and replacing them with math. I mentioned in the last video, one of the most important strategies that I can think of in mathematics is substitution, the ability to replace one thing with something else. That works for words here too, for definitions, for variables. So whenever we see jogger's heart rate, we should be just as correct writing either Q, which is the output variable, or R of S, which is the function notation way to write that output. And so if we're using function notation to do this, then I think what we're really looking at is, get a new color here, so use function notation. So we know that we're looking at R of S, that's our function name, but instead of just any old speed, we're looking at 10 kilometers per hour. So now instead of just saying r of some generic thing, I'm actually going to go ahead and write this. It's fuchsia versus, I don't know, kind of a lavender or something there. Anyway, colors are not as distinct as I might hope. So r of 10 is an expression that represents what we get out of this. If we didn't have that table, then we'd kind of be stuck. But the thing is, we do have, if we notice at a speed of 10, we've actually got a way to, let me get myself a box here. So we have a pairing in our table that matches up a speed of 10 with some kind of output. If we had asked for 12 or 20 or something like that, it turns out this function would not have an answer. Just because we can kind of mentally fill in the gaps doesn't actually mean that we can do it necessarily. And one of the phrases here completely defines this function. That's one of the ways I'll try to indicate that we really can't fill in the gaps here. These 5 points are all this function knows. But fortunately, we picked one this table does know about. So we picked 10 as an input, and so the output of that is going to be a nice predictable number. So when we go back to our table, here is the output at an input of 10. So I can say that this is 132. Now the scientists would really want me to put units on that too, so we could put beats per minute, 132 beats per minute. That would be the most fully fleshed out way to express this, but I'm a math guy, so I'm gonna resist the urge and just leave that without units. Okay, we are supposed to sketch the graph of Q equals R of S. Label all axes and points. So as is typical, we're going to try to be consistent about using our input variable for the horizontal axis. So in this case, S is our input and Q is our output. So there's our labeling. We're going to try to make some tick marks that seem to make some sense here. So our S values go, it looks like if we made them in 5s, we'd be pretty good. So we don't have to do 1, 2, 3, etc. I'll try to make them some vaguely convincing. Uh-oh. This is why it's good to have undo. I was going in 10s, and then all of a sudden I decided I wasn't going in 10s anymore. So 10, 20, 30. Of course, we don't actually have to get to 30. We don't have a value that large. But that should account for all of our inputs on that axis. And then these values go up to about 172. I don't really want to label 172. Maybe we'll go up to 180, and then we'll just kind of cut it into pieces. So half of that is 90, and then maybe we can make some little halfway values. Right, so this is not unique, but it will allow us to get all of our function graphed in this one little area. Okay, so now let's start graphing. When we are graphing from a table, we're pretty much guaranteed to just get a bunch of points. They're not going to be connected in any interesting way because all we've got are these 5 distinct little spots, these little pairs, without anything to fill in the gaps. So for instance, our first one looks like 0, 60, our input of 0, output of 60. So 0 means no left or right movement at all down here. And then a 60 input, let's see, these are, that's about a third of the way there, so that looks like a good first point. And then we're going to flesh the rest of these out. So 5 and 105 is going to be a little bit above that 90 mark. We've got 10 and 132, going to have to kind of eyeball that one a little bit, just a little bit below 135. 15 and 150. And then the one that's going to mess me up because it skips all the way up to 25 and 172, I'm really going to have to kind of guess where that one goes, but 25 and 172 is maybe there-ish. So if I'm being super responsible, I will try to label all these points. What was that, 105? 5 and 105. We had the point 10 and 132, 15 and 150. And last but not least. Okay, so our function as defined is just these 5 points. They do make a super tempting little curve there, but we're going to resist the urge. What is the domain of R? Well, now that we've got a visual perspective on it and a table, you kind of can pick your poison for how to interpret this. But domain is a list of all the inputs, and all the values this can take on go 0, 5, 10, 15, and then just to keep you on your toes, 25. 20 is missing. And then our outputs, so our list of all the possible results that can come out of this function is our image, and those would be a list of all these second components. So 60, 105, 132, 150, and 172.5. And unlike the last table we saw with the animals and the ages and all that, there aren't any repeats here. So there are 5 inputs and 5 distinct outputs to go with. Okay. this you start to get a little bit suspicious here. So this is a in theory brand new function which we are calling capital R of S, and maybe that's worth a quick little note. So lowercase r and uppercase R are not necessarily the same function, or even related mathematically. They don't have to be. And that's mostly just because, let me get a mess of that lowercase. So in mathematics, capitalization tends to create a distinct creature. So, in English, it's just another version of the letter signifying, either a proper noun or beginning of a sentence or something. But in mathematics, little r and big R could be totally different things or related in some subtle way. So technically, capital R of S here is completely different from, scrolling back, to this lowercase r of S. Now, you're just getting to know me here, but I am not a vindictive person. I am not trying to do this just to label these two things in a very similar way and diabolically hope that it messes you up. But in theory, they don't have to be anything different. We'll see the connection here in a minute. So in this plane, let's take all the points for little r of S that we had just a minute ago. So I think if we do that, and we're supposed to plot them all above here, then we've got a kind of probing question to tackle. So 0, 60 was one of the points from the previous function. I'm going to use that same green that we had before. 5, 105, 10, 135, 15, was it 15? Did we have 15? 15, 150, we did, yep. And then 25 and 172. And I'm going to be, I'm going to anticipate the result here. So clearly something interesting has happened. All 5 points that we had from the table have fallen onto this new curve. But here's the thing. So even though all those points fall along that blue curve, why is it true that little r and big R are different functions? So I guess the first argument would be, well, why would you think that they are the same function? So all points of little r fall on the graph of big R. So there's kind of the devil's advocate perspective for maybe they should be the same function. But remember, if you think back to our very beginning, a function is more than just the rule. It's a rule along with this pairing of domain and image. So the challenge is, and maybe I'll turn this into a comma, however, they do not have the same domain. And I think I can make that argument just based on the fact that looking at this graph, there are a whole lot of points, infinitely many, uncountably infinitely many, it turns out, points along this blue curve that are not part of the green dots. Anytime you pick the S equals 20 or 19 or 10.5 or pi or whatever you want to pick there are all these points that are part of the domain of this blue function that are not part of the domain of the green one. And if you don't have domains that match, they can't be the same function. Okay, so with that disappointment behind us, now let's use the graph to determine the image of R. So if we look at this function, we're going to say, what possible outputs could fall out of this? Now, keep in mind, we don't have a formula, we don't have a table, so all we have is this picture to go off of. But if the image is a list of all those outputs, what I'm really looking at is, what is the total possible kind of numbers that could appear along this q-axis? And what I see is it cannot go below 60, and then it rises to the right, and this arrow implies that things just keep on trucking that way. So this is just going to keep increasing as it goes to the right without any particular upper bound, no ceiling, as it were. So if that's really true, if that interpretation is correct, which it should be because we haven't been told that there's some kind of cap here, then this is going to rise from 60 and just keep on going. So there is not going to be any highest value. And so the way that we would try to write that would be, we've got image. Okay, so I want to use interval notation here, which may help remind you how this works. So interval notation looks like the lowest value you could get to, which in this case is 60. And then the highest value we can get to, which here is pretty much infinity. There really isn't a highest value. And so that's the way we recognize this. Because we can get to 60, we use the square bracket. That means we include this endpoint. And kind of we use a parenthesis to imply we cannot include that endpoint. We always do that for infinity. It's kind of a courtesy. Infinity is not really a number, it's sort of an idea. So the idea that we could get to infinity and include it in some way is just kind of, I don't know, sounds vaguely inappropriate. So we're just going to be polite, do the courteous thing, and say we always use parenthesis for infinity. So just a written reminder of this. So the square bracket. So having that next to the 60 means that we include 60. And then having the parenthesis here means we are going to exclude. I'm actually going to make that singular because there's only one of them. So this implies that we exclude, we leave out infinity, and that's kind of just an acknowledgement that you can't really include infinity anyway. Who can tame this wild horse? Ugh, man. All right. So there's a reminder of some interval notation. Try not to confuse these for points, especially if you've got parentheses on both sides. We'll really try to make sure that the context is clear there. So just as a comparison, we could also write just using, my wrist touched it. It did not like that. We could also write s greater than or equal to 60. So this is an inequality, perfectly great. A lot of the time web work questions will ask for interval notation, and that's what this is going for. So maybe let me make a note so we can write that down. So there's a written record of it. So this is interval notation. Super. And then so that it doesn't get lost in the mess, here's the thing we're actually looking for. That image is our final answer. So let me make sure that gets a box around it. For how many values of capital R of S it is equal to 120. So this is asking us about R of S, so the output of this function. How many times would it hit 120? So again, we've only got this graph to go off of, so let's go ponder this picture in for a minute. If we take a look at this, what we're really actually being asked for here is a measurement, if you will, a sort of a cut across this graph at a particular height. Because when we're looking at function outputs, here's 120, we're basically saying how many times does R of S hit this height? So, and let me make sure we don't make this picture all messed up. So we're saying, look, if we look at a height of 120 and we just walk our way across this graph, how many times does that dashed line touch this actual graph? And it looks like it's exactly 1. It hits just there. And so that's what our answer is going to be. Just once. And right, they could have asked us a very mildly different version of this and asked us what S value gets to this height. And we'd have to kind of eyeball it. But it turns out we can do one better than that. So finally, you feel this sense of relief when you're finally given a formula for something. Although looking at this formula, you might not feel any relief because there's a lot going on there. My experienced students tend to like equations for things better than just about anything else. So if you feel that sense of comfort wash over you as you see there's an actual equation here, you're not alone. So here's our formula. It turns out this is actually the equation that's giving us that nice blue curve. And the question we're supposed to answer is, for what exact value of S is R of S equal to 120? So basically the question we could have answered before. Okay, so just like in our previous video where we looked at functions from formulas, we can take a look at this expression, R of S, on the left side there, and say, look, I know what that formula is. It's just this thing you gave me up above. So wherever we see R of S, we would be just as correct writing 60 plus 180 S over S plus 15. And here is, my handwriting is going to be a real weakness here. I apologize for the letter S and the 15s that look, or the 5s that look so much like them. I will really endeavor to do a decent job of differentiating those things. So really, instead of R of S equals 120, we're really looking at this whole expression in green, the thing that this Q came from, equal to 120. And then again, we have a new sense of kind of relief because it's not this abstract function thing. Now we're down to just variables, basically. And it turns out we're pretty decent at this. So we're just going to start rolling our way through the algebra here. We're going to take away 60 from both sides. So we have 180 S plus, make that 5 look very 5-like. So if we take away 60 from both sides, we're down to 60 on the right side. And then here is where we implement what I lovingly call the everybody hates fractions policy, which is basically, look, you've got this expression on the left side, it's got fractions, nobody likes them, let's make them go away. And the way we make fractions go away is by multiplying by whatever's in the denominator. You are not allowed to look like a 5, sir. Okay, there we go. So we're going to multiply all that. It's going to create chaos on the right side, but at the benefit of making this left side look a lot better. So those pieces cancel out, and the left side looks like 180. Ooh, that's not the color I expected. That's like going to take a drink of what you think is water and instead is Sprite. Okay, so this is supposed to be blue. Whew, there we go, blue. 180 S, and then we on the right side have 60 S plus, some quick math there. What is that, 900? I'm hoping. So now we're really down to a clearly linear equation, no more crazy fraction stuff going on. If we take away 60s from both sides to try to combine like terms, then we've got a constant left on the right side, and that's it, which is pretty decent. And then now we're down to dividing. So divide 120 into 900 on both sides, and I think we've got ourselves 7.5. Okay. So, almost forgot. There's nobody here to remind me. This deserves a box. Good work. Hey, quick reality check. So S equals 7.5 is a fine number. And if we only had this formula, we could plug in 7.5 for S and see if that really does work out. We could also kind of do a reality check back on our graph here. So if S was 7.5, that's exactly halfway here. Does that look like it hits our graph right at a height of 120? It looks to me like it does. So that's pretty encouraging as far as a result there. Okay. And last but not least, this is where our interpretation stuff kicks back in again, so I'm sorry about that. Write a sentence that describes your computation in the previous part, and we're supposed to include units. So what I'm going to try to do is give you sort of a template for this function interpretation. And it isn't perfect, but it should give us kind of a place to go with this. So you ever play Mad Libs? So it's like we're a fill in the blank kind of game here. So when blank is blank, blank is blank. It's the least interesting Mad Libs ever. But these things have very specific sort of roles that we can play. So when we know what some input is, and then this is the number value for the input, and then we're going to with units, then the output, whatever that variable is representing here, is going to take on some kind of number. So it's going to be output, and then we'll also include that with units. So in this case, the input for this function is speed. And the speed that goes along with that, or the actual number that we picked, so there's the numerical value, is 7.5. And if I recall correctly, the units on speed were kilometers per hour. So when speed is 7.5 kilometers per hour, and then here's our output. So the output of this function was heart rate. So that's what I'm going to put in here. That's the quantity we were measuring. And the actual number, we probably lose track of this a little bit because they gave it to us. It's been a little bit since we had to think about it. 120 was that output. So we're saying 120, and then units on that as well is beats per minute. Okay, so that is technically a sentence. When speed is 7.5 kilometers per hour, heart rate is 120 beats per minute. It may feel like it could be read in a robot voice, but that gives us a template for interpreting functions. So really, the kind of expression that we are interpreting here, red is too threatening. What could we use? Maybe green. So what we've interpreted is f of input equals output. And you notice this is pretty concise. There's a lot of not a lot of notation there for the kind of complexity that we have unfolded. And that's really what math notation is all about. It's about compressing things so we don't have to write as much, because mathematicians are lazy. And instead, we have these agreed upon ways of writing things so we can unpack them and have an actual statement in English about it. But in order to save ourselves time, we write in these compact notations that have all this information just sort of waiting to be revealed. But so we will revisit in our next section and continue to think about functions.